Backtracking search is very similar to the DFS. We are going to find the one direction and go deep into that direction until you find the one solution. If you cannot find it, it's gonna fail. If you can find the one solution, it stops. So you can write this backtracking search in recursive way. Whenever we make a recursive method, this is a traditional way. Like you have a method which calls the recursive helper method. The recursive helper method may have more argument, more parameters to trace the recursive work and to check the base case and goal test. If you see this helper method, there is a base case first. This is the base case to stop recursive calls. But this one, when assignment is complete, that means when we are done assigning all the values into the assignment. So this is a true base case. So we met the goal. If we meet the goal, then we are going to just return the assignment. This assignment, when it's passed, it starts from empty dictionary or empty set. If I pass the empty dictionary to the assignment, each time I'm going to try to assign new variable and value set into the assignment. And when I have a full list of if all variable got the value, that means it is done. So in this one, assignment is complete. You probably will check if I have all the variables here, all the variable got the value. Then second one, it is like what we did in the search unit 1. Like we are going to find the next variable to work on. It's like we pop it from the frontier. But there are multiple ways to pop or multiple ways to decide which variable to work on. So in the select unassigned variable, you are going to use some techniques. You can use the word checking or MRB or LCB or MCB, maximum constraining value, the whatever techniques you can use in this method. Then you're going to choose one variable to work on. In our map coloring situation, the regions are variable. Like for example, WA, that region is the variable. So if you choose WA, bar will have WA, the region. How about the value? In our map coloring, the color will be value, like a red, green, blue. So after you find the variable, you are going through the domain, like a red, green, or blue. So for each color, you're going to check if it's working or not. So in the CSP, that means constraint satisfaction problem, you can make like two things. One is variables, and the other one is constraints, like a list of the constraints or something like that. So in the constraints, we can think about the adjacent. So each adjacent region cannot have same color. So if we have adjacent, that's good. So as a constraint, I'm going to make adjacent and check it. And also the variables. If I keep all the domains in the variable, it is easier. So I can have like a region as the key, then all the colors as the variables, values, red, green, blue. This part is given in the shellcode. So from the variable, you are going to choose one of the key. Then if you find key, you are going to go through the values in the variables. And for each color, its value, you're going to check if it's valid or not. This part is checking in the is valid. It is saying the consistent with assignment given constraints. So in this case, our constraint is two adjacents cannot have same value, same color, or same value. So you are going to go to the adjacent of the current var, then you're going to check if they are already assigned or not with the same value. That is what is valid is doing. Now we are going to like a try. This is like a try part. We are going to give a value to the variable, then add it to the assignment. So my assignment is a dictionary here. So now if I give red to the WA as a value, now my assignment will have only one item with variable equals value. Then you are going to pass this assignment and update it. Because if I use red for the WA, NT, and SA cannot use red anymore. If you want to update, you can pass the updated variables. Updated CSP can be passed to the recursive call. Then you are going to get the result. We're going to use none or dictionary to check. So if the result is returning the none, that means it failed somewhere. So you are going to try next color. But before you try next color, you need to delete this assignment has. So remove a bar value pair from the assignment. One of the easiest way to do that is L keyword. So delete L. Then I can say assignment bar that I choose. Then you can restart with a new value. You can try green, then you can try blue until it works, or if none of them works, and it will return none at the end. So this is the backtracking search pseudocode we are going to use for this map coloring lab. If I use for the checking technique, I probably will randomly pick any next region, any empty region which does not have a value yet. So in this case, when I have A, B, C for candidates, anyone can be chosen, A, B, C, or D. How about if I'm using the minimum remaining use technique? Which region has a minimum remaining value? If I can use 4 different colors, so I already used red, green, blue, so how about R, G, B, and yellow? Which one has only one choice left or 2 choices left? B. Which neighborhood use red, green, blue? So if I use MRB technique, next one, next region, or next variable I need to work on should be B. How about if I use a list constraint value? That means it does not give affection to other region, A. If you look at the A will restrict only one region. B will give 2 regions. C has 2 undecided region, and D also has 2 undecided region. So only A is the smallest, the least constraining, so I can choose A as the next one. Depends on what technique you use. Next variable selected will be different. So I highly recommend to use all 3 techniques for this lab. This lab 1 is very simple, then very short. Also, you can use any technique and you can still solve it because it's a very small set.